So because of my own bias, even though I'm a mathematician, I did work for my PhD dissertation on celestial mechanics. These are the mathematics and the physics that underlie the motion of planets. You notice I use a lot of sort of astronomical examples in this class. Well, that's probably why. And one of the very first results, historically, in celestial mechanics was the laws that Kepler formulated in the 1500s. And this is one of them. And it's written out as a sentence. And our job is going to be to take this sentence that describes what's called Kepler's third law and figure out what it's actually telling us about orbital motion in an equation form. So I want to take the sentence apart and figure out what exactly is going on here. And along the way, what we're going to do is also make a distinction that is not the most important distinction in the world, but it's one that we're going to come back to a few times over the next couple weeks. The distinction in science between what is a variable in an equation and what is a parameter in an equation. It's a subtle distinction, and it's not always the most important one, but I did want to talk about it a little bit today. So Kepler's law says that the square of the orbital period of a two-body system is proportional to the cube of the distance between the two bodies. Okay. So this is a sentence, but this sentence is describing some purported physical law. And it's also describing it in a way that actually will lend itself to writing it as an equation as well. So we can enfranchise all of our skills that we know with how to work with scientific equations and units and all of that stuff up to this point, if we can figure out what exactly is going on in this equation. So first, let's just add a little bit of context. Let's draw a diagram. Drawing a figure is a great problem-solving skill. And when we draw that figure, we're going to figure out what this proportionality is really telling us. So first of all, what do we have? We have a two-body system. So think of this as maybe the sun at the center and the Earth on the outer circle here. And if we assume that the orbit of this body is circular, it need not be. In general, it will be an ellipse and not a circle. But if we assume that it's a circle, then Kepler's third law will tell us that the distance between these two bodies, if we call that distance r, and the orbital period, which is the amount of time that it takes to make one complete orbit, that they're related according to this proportionality. So here's the diagram. So let me first ask, what does proportional to mean? Yeah, when we're writing it symbolically, it's often written as this little sort of sideways. It's not even a Greek letter alpha. It's kind of a symbol unto itself. It's like somebody took an infinity symbol and they sort of chopped off the right side of it. So this is usually how we begin the process of writing down a proportionality, is we'll use this funny little symbol. And then in this sentence, we're told that something is proportional to something else. The first something is actually not just the orbital period, but it's actually the square of the orbital period. So how do I translate that into an expression? If t is the orbital period, then what's the square of the orbital period referred to? T squared, yeah. So I'll put t squared on one side of this little proportionality symbol. And on the other side of the proportionality symbol, I have another thing. Not just the distance between the two bodies, but the cube of the distance between the two bodies. So on the other side of my proportionality symbol, we'll put not r, but r cubed. So often when Kepler's third law is stated in a science text or something like that, this might be the way that it's stated. Because it really is illustrating for us a relationship between two quantities that we're very, very interested in relating together. And not only that, but two quantities that we could, if we had a telescope and some time, we could actually measure these two quantities. Namely the period, how long does it take for one body to orbit another, for instance, the Earth to orbit the Sun, or really anything else. And then also the distance between those two bodies. These are things that we could directly measure. And they also have reasonable, measurable scientific units. Like we could measure the orbital period, the length of time it takes to orbit in seconds. We could measure the distance between the two bodies in meters. And because of these, we're going to call those two quantities scientific variables. These are things that we could actually measure directly. And that they have units that are sensible somehow. That the units mean something. Kind of put that in quotes. But they're things that we could actually observe, t and r. And yet t and r are not exactly the same thing. In fact, they can't be exactly the same thing because at least their units are different. So if they are to be related together somehow by a scientific equation, we're going to need something in this equation which is capable of repairing the fact that if I just write t squared equals r cubed like this, I don't have an equation that makes scientific sense, because according to the work that we did yesterday, we know that a scientific equation is only scientifically accurate if the units on both sides are the same. Let's do the dimensional analysis on what we have here. What would the units of t squared be? Seconds squared, right? Because t is measured in seconds, and so the units of t squared would be square seconds, which is not really a unit that makes a whole lot of sense, but whatever. How about r cubed? Meters cubed, right. So meters cubed is actually a measurement of volume, which makes at least some physical sense, and yet still, we can't just set t squared equal to r cubed because the units are very different from one another. So how do we fix this? What do we need to do to this equation in order to make it so that these units even have a chance of balancing one another out? What else do I need here? What would be a way of solving this issue that we're having? The goal is to put something else in this equation which can cancel the units that we don't want and give us the units that we do want to make it balance on both sides. And it doesn't matter which side of the equation we put it on. Let's just, for the sake of picking a side here, let's just choose to put some constant over here on the right-hand side, some k. And this is what we call, and we're talking about proportionalities, we call this the constant of proportionality. And very often, these constants of proportionality have really oddball units to them. In particular, what units do we need to have for this k in order to make this an equation that has a chance of being balanced? What should the units of k be here? And whatever those units are, yeah, we need to introduce our seconds squared because we have those on the left-hand side, and we need to get rid of the meters cubed that we don't want on the right-hand side. So the units of this constant of proportionality are kind of crazy. Seconds squared per cubic meter. But in fact, we need that constant there, at least in the beginning, in order to balance the units on both sides of this scientific equation. And we call that a constant of proportionality. And because it's not something that we could directly go and measure, this k. It doesn't even have units of something that we could measure, seconds squared per meter cubed. We often call quantities like that in science a parameter instead of a variable. That there's something that comes out of our calculations, but they're not something we can directly measure. Those of you that are working in the biology lab with the bees and the imidacloprid right now, you come up with a standard curve, and you find the slope of that standard curve, and it tells you the slope in the Beer-Lambert law that we worked with yesterday. That slope is a parameter, because it's not something you're measuring directly, but you're taking a bunch of measurements of, let's say, concentration and absorption, and plotting them and getting this parameter from your measurements. It's not something you measure directly, but it's something that you could compute later on from your measurements. And as you found yesterday in your activities, the units of that parameter that you got were really crazy. There was something like liters per meter per mole or something like that. So parameters tend to have units that don't make a lot of physical sense. They're not things we can measure directly, in contrast to variables, which are really the center stage of science. They're these things we can measure directly and we try to relate together using some law or another. So now we've unpacked this sentence into an equation. And Kepler's third law can be formulated with an equation that looks like t squared is equal to k times r cubed. T and r are things that we could measure. K, on the other hand, who knows? We would have to get that from somewhere. We would have to use some observational data in order to give us a value for k. And really the only way to get a value for k is to use observational data, very often, in science at least. Kepler was able to come up with it theoretically. He figured out what k exactly was. But there are a lot of different parameters that even go into making k. And so for now, let's be simplistic about it. Let's suppose I want to know what a value for k in Kepler's third law might be. Well, the best option might be to just take any single data point which we might know In other words, any single value of t that we know is related to a certain value for r, and to use those values, plug them into this equation, and then solve for k. In other words, I'm going to use known values, known experimentally measured values for t and for r to find k. And for our example, let's use the one orbital two-body system, even though it's not exactly a two-body system, that we're most familiar with, namely Sun in the middle and Earth on the circumference. What is the orbital period of the Earth? How long does it take us to make one revolution around the Sun? 1 year, 365.25 days. By the way, why do I need that quarter in there? Leap year. Compensates for the fact that every 4 years we get an extra day in there. Yeah, it's not a huge deal if we don't put that quarter in there, but I like that quarter. And let's convert that into seconds, just by noting that there are 24 hours in one day, and that there are 60 minutes in 1 hour, and there are 60 seconds in 1 minute. 60 seconds in 1 minute. Let me grab a calculator and get that. Okay, so there's the orbital period of our Earth, assuming its orbit is circular, which it is almost, but not quite. And then we just need the radius, the distance from Earth to Sun, and that's what we called 1 AU. And from some of your previous work, you had 1 AU converted into meters. You had the conversion factor for it. What was it? Was it 1.296 or 4.2? 496 times 10 to the 11th meters. Okay, so we have this one single two-body system, Sun, Earth, and we know its orbital period, and we know the distance, the radius of that circle. And so if we plug those two values into our equation, we should get rid of the t and the r and leave us with just a k that we could then find. So if I put this value of t, 3.156 times 10 to the 7th, if I square that, what do you get? 3.156 times 10 to the 7th squared. Let's hit the square key on that one. So I get 9.959 times 10 to the 14. 959 times 10 to the 14. And that's, again, meters squared. Then taking our radius, the distance from Earth to Sun, taking this and plugging that into our radius variable, cubing it, so that'll be 1.496 times 10 to the 11th cubed. Okay, so putting in 1 AU for r and cubing it gives me that awful gigantic number on the right-hand side. And then going back to our equation, we know that k, our constant of proportionality, is going to be determined by the fact that if I multiply k by that 3.348 times 10 to the 33 cubic meters, I'm going to get 9.959 times 10 to the 14th square seconds. And so how do I find k? I just have to divide. 9.959 times 10 to the 14 square seconds divided by 3.348 times 10 to the 33 cubic meters. So now again we can see where our units for k come from, because we end up having to divide seconds squared by meters cubed in order to get it. And then if we actually carry that out, (2.975) times 10 to the minus 19. And again, this number has really no meaning in and of itself because it's a parameter and because it has these wacky units of seconds squared per meters cubed. its sole purpose in life, this number k, 2.975 times 10 to the minus 19, is to fill this gap in our proportionality, is to relate the square of the period to the cube of the radius. To fix the units, first of all, but second of all, to also fix the numbers, so that the numbers can hopefully accurately predict the relationship between orbital period and distance, or whatever other proportionality you happen to be working with.